and in this video you're going to learn about advanced EIGRP. Specifically, you're going to learn about the engine or the algorithm that runs EIGRP, EIGRP messages, tables, and modules, and anything else that you really need to know for the CCDP architecture exam. So let's go ahead and begin. EIGRP is a unique protocol because it uses a hybrid approach combining distance vector and link state characteristics. Combining these features makes EIGRP very robust and allows for fast convergence even in larger topologies. Like RIP version 2, EIGRP is a classless protocol and it allows for variable length subnet masks. Another similarity between the two protocols is their automatic summarization behavior. The algorithm that EIGRP uses is called dual or diffusing update algorithm. This is the engine that makes EIGRP such a powerful protocol. Dual operates based on a topology table that contains all the possible prefixes and information about how to reach these prefixes. You'll learn more about the topology table shortly. EIGRP is the only IGP that can perform unequal cost load balancing across different paths. This is accomplished using the variance command, which defines a tolerant multiplier that can be applied to the best metric, and that will result in the maximum allowed metric. For example, in this diagram, there are two routes with a cumulative metric of 100 to a destination and a route with a cumulative metric of 200 to the same destination. By default, EIGRP performs only equal cost load balancing, so it will send traffic across only the first two links, which have the metric of 100. If you wanted to send traffic over a third link, you'd want to set the variance to 2, meaning that the maximum allowed metric is 2 times the lowest metric, equaling 200. Traffic will then be sent proportionally to the metric, meaning for each packet sent over the third link, 2 packets are sent over the first 2 links because their metric is better.
EIGRP has 4 basic components, and these should already start looking familiar to you. It has messages, so messages flow to and from neighbors, EIGRP neighbors. There's 5 different types. We'll dig into that in a little bit. EIGRP has the dual algorithm. The dual algorithm takes the information from those messages and then processes best path and possible best path. Then all the information from the messages and the algorithms get put into tables. So these EIGRP tables hold the data from the algorithm and the messages. And then finally, the modules. These protocol-dependent modules support a variety of network layer protocols. So we're not limited. EIGRP is not limited to just IP. So with regards to messages, there are different types of packet formats. There's 5 different types of packet formats. First, there's the hello message. A hello message is basically a query out to anybody who'll listen, asking if anybody's out there. So a router running EIGRP sends hello packets by default, and it will send those packets out and hope for a return reply. And when it gets a return reply, it'll get that update. And that update contains all of the messages or all of the routes that want to be shared via EIGRP. Update messages are messages with a lot of routing information in them. And then there's the acknowledgement message, which surely you know about from other protocols, but it's simply acknowledging that, yes, I've received your message. And that's key to the reliable nature of EIGRP, which we'll talk about in a minute. There's a query message. So if EIGRP loses a route and does not know how to get there anymore, it will query its neighbors saying, do you have any information about this route? Because I'd like to get that information. And then if a router does have information on that route or on that path, it will reply back saying, yes, I do have information, and here it is. So these 5 messages can be broken out into 2 categories, some that are reliable and some that are not reliable. The reliable messages use reliable transport protocol. And this is unique to EIGRP, but RTP basically makes sure that packets get to where they're supposed to go in order. So an unreliable packet is a hello message. That message is not reliable, but the update message from an EIGRP router does use RTP. So it is sequenced and there are acknowledgments. So there is an acknowledgement to that message, but the acknowledgement itself is not reliable. Then there's the query message. Remember, the query is to ask, do you have information about this route? And that uses RTP, and the response to that query, the reply, also uses RTP. So 3 different types of messages use RTP: the update, the query, and the reply. And I think that's critical to know for your exam. Now let's talk about the EIGRP algorithm, which is dual. Now, to understand dual, you need to understand what successor and feasible successor routes are. When you think of successor, just think of success. That's the best path. So if EIGRP loses connectivity to the best path, it will then run the dual algorithm and ask, is there a feasible successor? Is there a second best path? And if the dual algorithm states, yes, there is a feasible successor, a second best path, it will then promote that second best path to the best path. So that becomes the successor. Once it's the successor, it is then installed into the routing table. So for example, it would be installed into the IP routing table. And then the router would begin to use that new path. So this chart gives you an overview a high-level overview of how the dual algorithm runs. But it's important to know these concepts of successor and feasible successor as you move forward with EIGRP and how dual uses that information.
Now, as stated earlier, a key table to understand is the EIGRP topology table.
Topology table contains all destinations advertised by neighboring routers. This includes, remember, the successor and feasible successor routes, the best path to a destination and the next best path, respectively. So topology table is key for EIGRP to run. Now remember, within topology table, you can see the route tags. So in EIGRP, you can actually perform route tagging. And all you really need to know for now is that you can identify routes by their origination, which allows for custom routing. So you can tag those routes with a manual entry. So that's all you really need to know for now. But getting back to EIGRP tables, now, here's an example. We have, again, a hub and spoke design, router A, router B, and router C. Now, router A is going to build out, as soon as it enables EIGRP, it's going to build out these EIGRP tables. And one of the tables, again, is going to be this topology table. The topology table is going to contain critical information for EIGRP to run and make the choices upon what the best path is going to be. So in the topology table, it's going to insert routes that it learns from router B and router C. And then it's going to ask, now that I know about this route, which neighbor did I learn it from? And then finally, it's going to say, all right, I know the route, I know the neighbor I learned from, what metric should I assign to it? Which way should I send traffic or forward traffic? So in this example, the route itself, let's say we'll do a 10.1.1.0/24. And let's say we learn this route from both router B and from router C. So this topology table is filled out with 2 entries for the same route. Again, this is not the routing table yet. This is the topology table. And it has a metric, so let's keep it simple. So the metric to router B is 10, and the metric to router C is 20. So for this simple example, let's just say that the router now realizes that the successor route, the best route, is going to be the path through router B. Now, once the dual algorithm has run and it realizes this, it then takes that route or that path and it places the successor route into the routing table, in this case the IP routing table. So now we know the successor is to router B and the feasible successor path is to router C. So as we can see, it's going to choose the path out to router B. Now, what happens if this route information is lost and router A no longer learns about this route from router B or from router C and it gets flushed? Well, router A, what he's going to do is he's going to send a query to router B and to router C asking, do you know about this route? Because I've lost it and I'm hoping you have information on it. And the neighbors will respond back, but specifically, let's say in this case that router C is the only one that knows about it. Router C will respond, yes, I'm aware of it, and it will send the information over, and router A will say thank you very much, and router A will then insert it into the topology table. It will become the successor, and once it's the successor, it will be placed into the routing table, and then router A will then begin using the path through router C to reach that subnet. And last but certainly not least, we have protocol-dependent modules. So EIGRP and the dual algorithm function in a way that protocols can run and use EIGRP independently of one another. So IP builds out its own neighbor and topology tables. IPX and AppleTalk, they all build out their own neighbor and topology tables, and dual can work with any and all of them. So neighbor discovery and updates are a big part of EIGRP, and the best way I can equate this is if you have a new neighbor who moves into the neighborhood, you surely knock on his door and you introduce yourself and you tell him about yourself. Maybe you're married, where you're from, what your interests are. You tell the neighbor a lot about yourself, and if your neighbor is friendly, they're probably going to tell you a lot about themselves as well, like where they're from and what they're interested in as well. So in that initial conversation, a lot of information is exchanged. When you see that neighbor in the future, you don't give them all that information again. You just give them an update. You just say maybe what happened to you in the past day or so. So EIGRP pretty much works the same way. When two routers establish an EIGRP neighbor relationship, initially there is a major conversation where a lot of information is transferred between the two routers. And then there are follow-up conversations after that just have incremental updates. So the best way for me to describe this to you is actually just to draw this out. So let's say here we have router 1 and router 2, and let's say they're sharing the same point-to-point circuit, and both of the interfaces, directly connected interfaces for router 1 and router 2 are both participating in EIGRP. So router 1 sends a hello packet over to router 2, and router 2 receives that, and router 2 sends a hello message over to router 1. And this neighbor relationship now comes up in EIGRP. Now, initially, there is a large transfer of routes saying, hey, I have a lot of information to share with you. And router 1 says, you know what? You don't know anything about me. I have a lot of information to share with you, a lot of routes to share with you. Now, these hello messages continue repeatedly over and over. So the routers know that, hey, I know you're still around and I know you're still up and running. And they're consistently checking to make sure that they receive these hello packets. But let's say router 1 has a new update, a new subnet they know about. They're just going to send information on that subnet. Or let's say router 2 turns up a new interface and they insert that interface into EIGRP. Let's say 10.1.1.0, it's a /24. Well, router 2, when they send an update to router 1, they're just going to send this one update. So again, it's like the conversation with your neighbor. You're going to have one initial conversation about a lot of things, but then your follow-up conversations are pretty much just going to be updates. That's pretty much how EIGRP works. Now, the default for high bandwidth links, the hello interval is 5 seconds, the hold time is 15. For low bandwidth, the hello interval is 60 seconds, and the hold time is 180 seconds. But for the example here, let's say we need to know faster than 15 seconds if a circuit is down or a neighbor is down, and that we no longer want to forward routes, and we want to tweak that. Well, EIGRP allows you to do that. we can just log on to the interface, onto the router, and then configure the interface to change these intervals so that we are aware if our neighbor is down much quicker than the 15-second hold time. So the way you do that is that you go into the configuration, and then you go into the interface itself. So Fast Ethernet here, Fast Ethernet 1.1 is the interface on this point-to-point link, and IP hello interval EIGRP autonomous system number 10, and we're going to set that to 2 seconds. And IP hold time EIGRP 10, we're going to set that to 6 seconds. Now, this is important to note. Hello interval is important to note locally, but hold time is actually information we send on to the other router. And let's actually draw this out. I think it'll make a lot more sense for you. So here we have router 1 and router 2. And we have set router 1, the hello interval, to 2 seconds. So every 2 seconds, we will be sending a hello message over to router 2. Every 2 seconds. And again, we've adjusted that from the default 5 down to 2 seconds. Now, it's important to note we also set the hold time for router 1 to 6 seconds. And this hold time information is not actually held locally. We forward that over to router 2 to say, hey, you know what, router 2, if you don't hear from us in 6 seconds, then we're down. So here, we send you a hello packet. Router 2 counts down 6, 5, 4. Oh, I received a new hello because it's 2 seconds later. I'll begin counting down again. 6, 5, 4. I received another hello, and that resets my hold time counter, and I will begin counting down again. So every 2 seconds, these hello packets are actually resetting that hold time counter on router 2. Let's say router 1, the interface goes down, or the router goes down. Router 2 begins counting 6, 5, 4. He's not going to receive any hello messages, and he's going to count all the way down to 0, and he says, you know what, I haven't heard from you, you are down. That's important to note because now I'm going to flush your routes out of my table because I don't want to forward traffic to you anymore, because it's probably just going to get dropped, and therefore all of the information from router 1 is flushed out of the router 2 routing table. And that's important to know for convergence purposes, that you can tweak these numbers.
So here's what you've learned. You've learned about EIGRP algorithm, messages, tables, and modules, and any other key information you needed to know for your CCDP architecture exam. Good luck in your studies.